Thank you very much, and I apologize for not coming to Leon. I have a bit of sore throat these days. First, I'll tell a few words about Krzysztof, and I knew him during his IHES period, but actually twice. First in 1988, maybe one of earliest encounter. I went to IHES, I went to France for 1 month, and among this 1 month, I went to IHES for 1 week, and Krzysztof kind of knew already me, I knew already him, also works, and he was my main interlocutor at that time. And then when I arrived in 95, we already have, for 5 years, we were colleagues and very good friends. Yeah. Now, so we'll talk about resurgent structure of Chern-Simons theory. And in fact, about resurgence, the first time I heard this word, it was from some preprint by Krzysztof and Anti-Kupianin when they had some ideas about renormals. Now I'll tell you my story. Now, okay. So what is this resurgent package? And actually, resurgence could be. Oh, sorry. Go back. Okay. Resurgence could be kind of complicated thing, but typically what we have in practice, it's simple resurgence, and it consists of several things. You get just some collection of complex numbers, could be finite or countable, all distinct numbers, and in really interesting situations, you have everywhere dense subsets, and for each number, you have a formal power series in a Planck constant, which is a divergent series that terms go like factorial, times exponential term. And then the third part of the package is a collection of integers. It's called indices for each ordered pair of distinct points, the alpha. And the property is the following. So first you make from each alpha you get convergent series. You divide by factorial, and you get series because by the exponential growth converging in some neighborhood of 0, but we shift variable. So we consider the series centered point z alpha. So we get germ of analytic function z alpha. And then this germ should have endless, for each point alpha, should have endless analytic continuation, singularities of the form. Then approach another point z beta, say. Then you get a holomorphic function and something which jumps by integer multiple of function phi beta at this point. Yeah. Okay. Yeah, so that's it. So you get functions. So essentially, if you know one function, you go make an analytic continuation, you will see some, it goes around some point, have some jump, you get another function, and you continue the things, and usually you exhaust all functions from your collection. Okay. Sorry, it's a bit, yeah. So we start, if we start at some point, and now we make an analytic continuation along straight trace emanating to the point, then we extend to some star-shaped domain. We will show next slide. It should be complement to infinitely many cuts, starting from other points. Maybe I just show you this picture of this guy. Yeah, you start. You have this. You center yourself at point z alpha. There are other points, and several of them can be aligned and stay in the array. And you make infinitely many cuts. So what happens? You should have a cut at discrete subset of z, of complex numbers. That's on the condition. Okay. Yeah. So you get function extend to the complement of infinitely many cuts, and the points when you make cuts are not all possible singularities of your functions. as I explained to you, this all possible singularities could be everywhere dense set. And for each point, you'll see maybe some only discrete subset of C. And how to reconstruct for this analytic continuation kind of original divergent series. You took a generic direction, which doesn't go through the cuts, and make a Laplace transform along this guy. And you formally substitute this 1 over factorial, the factorials will disappear, you get something which has asymptotic expansion of your original form power series. Yeah, so you get many functions which are defined in sectors in H-bar plane. Yeah, here one assumes that integral is convergent. And that's the way how people using this Barrage summation and endless analytic conversion reconstruct some analytic function which has this divergent expansion. Okay. Yeah, so we get now so the software is a bit slow. Yeah, so get again this picture, these cuts, and then okay. Yeah, so what you get multivalued functions. You get infinitely many branches, and the monodromy structure is encoded by some Stokes indices for all ordered pair of integers, and usually they're skew symmetric if no three indices, no 3 points are aligned. If it's not, if they're aligned, it's a bit more complicated. What is the structure? Again, in a simple situation, when the set of singularities is discrete, for example, it's finite. And in all examples in my talk, we'll have discrete subsets. We obtain a local system on C minus complement to this finite or countable subset. And with a fiber, with sum of copies of integers over all points. So if we have infinitely many points, we get infinite rank local system, but countable dimensional. And in general, what we get, if it's even the set of singularities is not discrete, you get locally constructible sheaf of at most countable free abelian groups. And simple resurgence is a homomorphism from this sheaf to a sheaf of holomorphic functions in Borel plane. So it's branches of functions and some linear relation between branches. And if you imagine that you don't know what is analytic continuation, how to see kind of numerically these properties of resurgence. Suppose we have two closest singularities. Suppose we have like finitely many or countably many singularities, and two singularities are in 2 points are close to each other. This the smallest distance between them. Then each of singularity, this jump will contribute kind of to the behavior of coefficients of another thing. It will be leading term behavior, and then we'll have the following asymptotic. If we have point expression point alpha, we get coefficient C alpha k. You divide by factorial, cancel this exponential term, so it will be of polynomial growth. So you get some sequence of polynomial growth depending on k, multiplied by 2 pi I, because in jumps we divided by 2 pi I. And the things will have asymptotic expansion that can go to infinity, which is controlled by small coefficients, kind of low coefficients, not very high index, but low index coefficients for it's another point. So the leading term will be CB0 divided by chi, and then next term will be CB1. It's just expansion of logarithm multiplied by monomials at other points, gives us this formula. And vice versa. If you look the large K asymptotic of coefficients of series at point ZB, it will be controlled by series in A. So in a sense, resurgence can be said the following. You start with your series, divergent sequence of numbers, divided by factorial, make expansion, get another sequence. Now again, divide by factorial, make expansion, and you get back to original sequence. So that's one of origin of resurgence. But also here, one can look on kind of the first leading coefficient. The growth, it's 1 over k, yeah, divide polybase control. Constant, and then one can make this following prediction. You just consider series in 1 point and the alpha, consider k's coefficients divided by zeroth coefficient, multiplied by this power k, divided now by k minus 1 factorial. This guy will have, the claim to this guy will have some limit. Calculate limit at second point. We have two numbers, and the product will be 1 over 4 pi square times the square of integer. Yeah, that's a corner of resurgence. The square of integers will be the square of Stokes index, because it's anti-symmetric, and get 2 pi I, and it works in reasonable examples. So you can calculate Stokes integers without going to this very high precision expansion. Just calculate like very approximately limits. You can calculate the Stokes indices up to sign. Okay. So what is geometric source of this simple resurgence structure? It's actually very natural. It's come from when consider exponential integrals, integrate something divided by h bar with functions with more singularity. Suppose we have a smooth complex variety. Sorry, I can repeat myself. So smooth complex variety. I meant to be algebraic variety, but it's not necessary. With a function, holomorphic function, and volume element. And it's capital N is dimension of a manifold. Now we can try to write exponential integral. So you take exponent minus function divided by h bar times volume element, where h bar is complex number, non-zero complex number, and cycle of integration is essentially class in homology group of pair. You have your variety, and you can see part of pullback of under f divided by h bar of numbers close to plus infinity. Yeah, so where this exponent minus f of h bar will be very small. So what are algebraic examples? So there are algebraic examples and not algebraic examples. In algebraic examples, all guys, variety, functions, volume element are algebraic. So the first things which you all know, it's Gaussian integral. You integrate over Rn, but Rn is part of Cn, so variety is a complex vector space. Function is sum of squares, or half sum of squares, volume element is usual volume element. And then if h bar is positive number, you integrate over Rn, and you get square root of 2 pi h bar per n. And then one can do a little more complicated integrals, not squares, but for example, consider cubic polynomial, then you get any function. Or you take C star, you get x plus 1 over x, you get b. Up to some simple corrections. And this exponential integrals with more complicated polynomials are also prominent in mirror symmetry for mirrors for Fano variety. And the basic examples, mirror for projective space. You consider projective space of dimension n, you consider n-dimensional torus, and the function of the sum of coordinates and plus 1 over product of coordinates, and to take multiplicative volume element. And then if you calculate integrals, it will be responsible for Gromov-Witten invariance for projective space. But I will not talk about mirror symmetry at all. Okay. So. Yeah, let's assume the following for my variety, that all critical points are isolated Morse in holomorphic sense. So this Hessian at each point is non-zero. And assume that also simplifies the life as all critical values are pairwise distinct. And this third condition is kind of topological. There's no critical points at infinity, which means that essentially there exists a computification, partial computification, x bar of x, such that f extends to this proper map. So fibers will be compact. Volume form can have poles at infinity, doesn't really matter. And such that this, for this proper map, near infinity to the locally trivial bundle. In fact, trivial bundle because C is contractible. Yeah, then for each critical point and a generic direction, we have a canonical homology class of Lefschetz symbol. Lefschetz symbol, it will be sub-variety diffeomorphic to Rn of middle dimension, going to infinity, and it will be union of setting gradient trajectories of real part of exponent minus I theta f with respect to essentially any Hermitian metric you should a little bit be careful to infinity. And it's well defined up to sign. It's a choice of orientation. So the next slide will be some picture of these Lefschetz symbols and how they project to domain of values of function. So if you consider the gradient lines for Hermitian metric, this gradient trajectories they're parameterized by sphere and n-1 dimensional sphere of vanishing cycles of my function, and all the spheres project to a point, and so get a Lefschetz symbol project just to a straight ray in a plane, and if it's generic direction, the straight ray will never pass through other critical values. Okay. Yeah. Now, for each critical point, we define normalized integral. So we have this integral exponent minus f over h bar, times volume element, but it has some kind of leading terms which we want to cancel. So it has this critical value is the alpha divided by h bar, multiplied by exponent, so cancel exponential growth. And then when h bar goes to 0, we get also square root of 2 h bar usually appears in Gaussian integral, you divide by this guy. And then we get something. And this is an analytic function of h bar defined outside of Stokes rays. Because if you're outside of Stokes rays, your Lefschetz symbols really goes to infinity, doesn't stop at a critical point. And the asymptotic expansion in h bar is a form power series, which depends. So you get a form power series for each point, which doesn't depend on the direction, on the Stokes sector, because you can you choose different Stokes rays and complement to Stokes ray, you get different integrals, but form power series will be just the same. And you calculate it using kind of Taylor expansion of f at the critical point using usual big formula. And it's completely algebraic calculation. Okay, so I get this. So from geometric perspective, we get automatically analytic functions and sectors which have asymptotic expansion given by this form power series. And in fact, two viewpoints are equivalent. One can go to the endless analytic integration and make it Laplace transform, or go directly to this geometric construction. You have the same actual analytic function sectors. Yeah, so one can describe this, instead of endless analytic integration, one can say the following. If one grows a Stokes ray, so the argument of h bar will be a different direction from the alpha to the beta. Then integrals e alpha will change by this actual integral will jump by exponential small terms, which will not affect form power series. It will be exponent minus differences of critical values divided by h bar. It will be very small real numbers along the ray. Multiplied by Stokes indices, multiplied by this a beta integrals related to other sides. Now, so from this perspective of exponential integrals, the Stokes indices are number of gradient lines if there's nothing in between. And so the picture is the following. If you consider direction which is not a Stokes ray, like green direction, you get this rays in the image of map. In the pullback, you get some Lefschetz symbols. Remember, this high-dimensional objects are RANs. And if you rotate direction, you go to, let's say, red direction, you change homology classes of Lefschetz symbols. The guys which correspond to things on the right will not change essentially homology class because they move continuously. But things which go to the left will change by some integer combination of other cycles. Okay. Okay. Yeah. So there's kind of going back to examples, if you consider a reintegral, this cubic polynomial, there are two critical values, minus 2/3 and plus 2/3, and form power series you can easily calculate. You get some hypergeometric series, divergent hypergeometric series, and Stokes indices are plus and minus 1. And similarly, for Bessel function, you get a little bit different hypergeometric series, and Stokes indices are plus and minus 2. And that's actually explains why area and Bessel functions are so important. It's kind of really simplest examples for resurgence. You cannot have resurgence only with one singular value. You should have at least two. So 2 is a minimal number, and minimal trivial Stokes indices are 1 and 2. So it's really basic examples which come from kind of topology, and that's why they appear everywhere. And even on this example, one can check that if you consider divide by factorial coefficients on one series, make a asymptotic expansion, you see it's controlled by low indices, low coefficients for another story, and vice versa. And now I'll go to the next example, which is Stirling formula. And I think it's really, it's kind of new example. I think it should be really the best, really the first example for resurgence, and very nice one. Yeah, so the variety is complex line, but function is not algebraic. It's point of x minus 1 minus x. And volume element is dx. You can consider what is a critical point. You get like point maybe 0, yeah? Yeah, you get point 0. And now you can make this integral near point 0, get what you do essentially, if you do simple manipulation, you see that you get Stirling formula. You want to study asymptotic expansion, and when n goes to infinity of n factorial divided by usual leading term n to power n exponent minus n square root of 2 pi n. N will be inverse to h bar, or h bar inverse to n, and then you get a series. These numbers are not Bernoulli numbers. 1 of 12, of course, is Bernoulli number, but the next one is not. The logarithm of Stirling series are Bernoulli numbers, but these are some other numbers, called Stirling numbers. And the claim, it is a path of resurgent package with infinite set of critical values, which will be 2 pi I integers. It will be actually critical values of this function f. And all series, but all series at all points are the same series. It's just the same geometric series with these numbers, 1 over 12, 1 to 288, and so on. And resurgence implies this interaction of two nearby points. It implies asymptotics for this normalized Stirling numbers. You divide by factorial, then multiply by, oh, sorry, it should be 2 pi to power k. It's misprint, it's 2 pi to power k. So the usual we have to normalize numbers. In fact, it will be a bit more too complicated because for each point we have two nearby points. And for point 0, get point 2 pi I and minus 2 pi, which are closest. And so you get slightly funny behavior. You consider this normalized Stirling numbers for even number k, very large number k. You consider asymptotics. And then it's controlled by normalized Stirling number for odd k, like 1, 3, and so on. And conversely, if you consider asymptotic things for odd k, they control by these things for even k. Yeah. Now that's a very simple result, but it seems to be new. Okay. Yeah, so what is this example? It's not algebraic example, yeah? You have exponential function minus 1 over x. In fact, one can understand this thing is following. This variety x is infinite abelian curve algebraic variety, which is C star. The function in which you consider is a primitive of the pullback of closed algebraic one form on y. This is the 1 minus 1 y over dy. And the volume element is pullback of algebraic volume form on y, which is dy over y. Yeah, so you just consider covering C star with this logarithmic story. And on abelian covering, on universal abelian covering, any one form will be exact, so we get it will be differential of function. And yeah, so it's another class of examples. After algebraic varieties and functions and volume forms, you get closed one forms and volume forms. So this set of critical values for this covering is a finite union over over zeros of one forms of torsors of finitely generated group. It's the periods of your one form on your variety. Just in this simple example, of course, periods are 2 pi I, yeah, multiples of 2 pi I, get just one arithmetic progression step 2 pi I. And recently with Jan Sobelman, we developed a general theory. So for this variety with one form, we proved that you get gamma equivalent resurgent package with infinitely many critical values for this, and the nice thing is the genetic series for Stokes indices. You get infinite sequence of integers, or integers labeled like by 2 points. In fact, genetic series are rational matrix valued functions in several variables. So one can effectively calculate everything, both Stokes indices and form power series expansion by computer algebra. Sorry. Go. Yeah. Now go to quantum Chern-Simons theorem. So it's start with three-dimensional latent complex compact variety, and this infinite dimensional, my algebraic variety will be, or complex variety will be infinite dimensional. Consider like the three forms as well as an SL2C or any reductive Lie algebra or complex numbers, and function is kind of cubic polynomial in infinitely many variables. And I think it's actually this, we should consider this as a cubic polynomial in infinitely many variables with rational coefficients, whatever it means. It's infinite dimensional space, but coefficients which you see here, 1/2 and 1/3, is definitely rational. And eventually, form power series expansion will have algebraic numbers. So it's not just transcendental numbers, it's really kind of rational numbers are behind in some mysterious sense. Yeah, so this cubic form is in infinitely many variables, it's highly symmetric. In finitely many variables, if you get cubic polynomial, it usually has finite group, it never have continuous group, but here you get huge infinite dimensional gauge symmetry group. So we can go to the quotient by the group, and the group is connected component of the complexified gauge group. Consider space of smooth maps from your manifold to SL2C, and consider connected component. Why I should consider connected component? Because if the group of all maps has fundamental group Z, group of connected component Z, which is still acts on the quotient, but the section of Z doesn't preserve the function. It's changed this value by constant, which is 2 pi s squared. So to have actual function, we should divide by connected component. Again, comparing this story with situation with one forms and coverings, we can see that this X prime is covering of the quotient, yeah, X0 over Z, on which you have just one form, this period. But the quotient is not, it's kind of a bit strange. It's not algebraic because you divide algebraic variety by the group. It's not algebraic variety. It's some kind of strange thing. But critical points on the quotient are flat connections, you get flat curvature, and usually there are finitely many flat connections. Yeah, so it's very similar to the situation of algebraic variety with one form. We get like finitely many zeros of one form. So what are critical values? Critical values of my functions will be union of finitely many arithmetic series with step 2 pi s squared, and as explained, because this whole thing is kind of invariant under deck transformation, like in the case of algebraic one forms, I get only finitely many divergent series corresponding to this flat connections. And so the whole resurgent package is equivalent with respect to group 2 pi I squared Z. now, what we can say about this resurgence package? First there is a physics perspective, because it's kind of infinite dimensional integral, field theory, one say. So the divergent series are given by standard perturbation theory, which is actually well defined. It was figured out in the early 90s by Scott Asselrod and Isidore Zinger, and independently by myself. So all integrals of in perturbation theory are really well defined, convergent, absolute convergent. In principle, one can work with this, but only in principles. Nobody ever calculated seriously this divergent series to infinity. And also there are Stokes indices. And Stokes indices namely says it's a number of gradient lines in some infinite dimensional space. And gradient lines, it's maps from real line to space of connection, so you get some object in 4 dimensions. And this equation of gradient lines turns out to be what's called Kapustin-Witten equation. And if you go from one flat connection to another flat connection, so it means that you put for the Kapustin-Witten equation some boundary condition at plus minus infinity. The things approach to flat connections. And here, I don't even want to think about how to start this thing rigorously, because there are huge analytic issues with the compactness of the space of solutions. And it's only like idea of what it should be. So both type of data, series and indices, are very hard to access effectively. I want to say that this perturbation theory, one can do maybe first, second term, but one cannot do all terms simultaneously. It's high and high dimensional integral, so it's not something which we understand mathematically. Yeah, but then in 88, Divergent proposed what should be a partition function for unitary Chern-Simons theory, which is integral of space of unitary connection, which is kind of half-infinite, half-dimensional, infinite-dimensional cycle in the quotient by shifts. In terms of representation theory of quantum groups, it's root of 1. And the Planck constant for this unitary Chern-Simons theory should be quantized. It's not just any number on any sector. It should be 2 pi r over integer. And the integer is called level. And why it should quantize? Because the expression 1 over h bar Chern-Simons to be all defined on the quotient. Because Chern-Simons defined up 2 pi I squared. The exponent is well defined only if h bar is of this form. But for me, it will be also said that it lives on the larger complex space, complex valued connection. It's also exponent 1 h bar Chern-Simons will depend on the larger space, not only with cycles integration. And the cycles integration is not a priori Lefschetz symbols. And one can argue that that integrals over U should be equal to formal integral linear combination of Lefschetz symbols. Essentially, one can make a contraction, and this integers which appear as integer linear combinations are again heuristically number of solutions of Kapustin-Witten equations, so that on one end you put boundary conditions which is a flat connection, and another infinity you put boundary conditions that's a unitary connection. And then again, huge analytic issues of compactness, but this should be this integer number which we are looking for. Okay, yeah. So theoretically, from physics, we get also answer. This partition from Chern-Simons should be something coming from these Lefschetz symbols. But now I will tell you about mathematical perspective, which gives me effective controls of both series and Stokes indices, at least in simple situations. So what's the main idea? Yeah, first of all, if you use any triangulation of manifold, one can rewrite this Witten-Reshetiv-Derived answer for what is for unitary partition function in unitary Chern-Simons theory as certain finite sum. And finite sum of kind of very general nature. I'll write some specific form, but we believe it more natural. General, and I don't know how to what's the better name, beta sums or num sums. Werner now considers something similar, but refer to beta. So it's expression like this. What will be the simplest expression of num sum, beta num sum, which is worth to study? You consider for each level k, you consider q is this primitive root of 1, closest to 1, exponent to pi over k. Then you get sum of all integers from 0 to k minus 1, you get 1 to factorial of L multiplied by, let's say, q to L square. Or can maybe q to 3L square, some constant. You get some, so you get some algebraic number which belongs to cycloatomic field and it depends on integer k. Or so more generally, you do things like this. You maybe have several variables, each run from 0 to k minus 1. You get product of q factorials and raise to q to some half of quadratic form in this guys. And in fact, coefficients could be not necessarily integers, could be rational. I think nothing depends on these details. And the claim that this sequence of numbers behave completely undistinguishable from what you see from tree manifolds. So all things which you try to have flat connections, gradient lines, and so on, one can see just for these numbers. But what I claim, when you see expression like this, you can immediately reproduce, which should be answer for your unitary quantum Chern-Simons theory. Also, just looking on this expression, you immediately can produce candidates for perturbation series and Stokes indices. How to do it? Yeah, so first, one consider, when you get expression like this, you associate with this multivalued function on many complex variables. You can see the sum of dilogarithms, say, and plus the linear form in logarithms. So these critical points correspond to, and critical values of this function correspond to those of Chern-Simons theory. As critical points, in general, Chern-Simons theory, as critical values, you get some very special combination of dilogarithms and called something called K3 indecomposable and some infinite rank group. And these numbers which you get from Chern-Simons theory, critical values for such expressions are exactly the same numbers. And for each three manifolds, one can write infinitely many expressions like this, giving the same critical values. Yeah, so you get that's the basic object. So you get this multivalued function. And what is prediction first of perturbation series? You consider exponent of this function and add a little bit corrections called quantum correction. I will explain in a second what is it. And make integral near critical point. For the critical point, the correction we add has only strictly non-negative powers of h bar, so the critical point is only controlled by f0. But what is this? What is quantum correction? You consider something called the Faddeev quantum dilogarithm. Consider asymptotic expansion of quantum dilogarithm. It will be dilogarithm divided by h bar plus this infinite series. Or equivalently, one can look just on your original beta num sum and try to see how this q factorial grows when x as j is number of unit circles corresponding to term of summation, and you get immediately this expansion. Just for num sum, you're obliged to see this asymptotic expansion. It's okay. Yeah, this everything is completely explicit. Critical points will be some algebraic numbers. It's the equation of critical points are algebraic equations, and one can do computer algebra and calculate, at least in simple example, when you get just sum with one variable, I can calculate perturbation theory up to 1,000 terms explicitly, precisely. So it will be actual algebraic numbers and not some approximation. And with this 1,000 digits, one can do, with this 1,000 terms, one can do a lot. I think one can essentially reconstruct all resurgence numerically. And, Yeah. So this is things which you can do really calculate effective to enormous precision. And what are Stokes indices? And the answer is eventually seems to be very simple, just number of gradient lines for this function f0 from one critical point to another, nothing else. It's actually simpler than I expected originally. Originally, it's part of some general product we have with Jan on floor theory and resurgence. And the original answer was in terms of pseudo-holomorphic disks. Yeah, for example, when I have my critical points, it can be interpreted as intersection of two Lagrangian manifolds, and I should count on pseudo-holomorphic disks, which is complicated. At least cannot do it. I don't know how to do it on computer, but it seems that in this situation there is some kind of simplification. One can reduce to one-dimensional problem, not two-dimensional, and reduce to gradient lines. So there's maybe such remark: holomorphic disks can be reduced. Calculus of holomorphic disks can be reduced to what's called spectral networks. And spectral networks start. There's some kind of ramification points of Lagrangian manifolds enter the game, and here there's no ramification points, and it seems that spectral networks reduced just to straight integrals, which are gradient lines. And with gradient lines, it's a really very elementary computer program which you can calculate, at least in case of one variable, very easily. In one variable, just really very easy calculation. And one can seek patterns, and this gives heuristically the complete prediction what are Stokes indices, again, in the simplest example. Okay, so at least in the case of one variable, kind of baby case, we have control of everything, completely effective control, and I think we are very close actually to the proof that it satisfies all the research. We have endless analytic returnation or jumps and so on. But what is going on? It's we have three examples. We start with algebraic varieties and functions, or closed algebraic, misprints, algebraic forms, or Chern-Simons theory. In first case, we have only finitely many critical values. In second case, we get critical values plus shield by finite rank lattice. In third case, also by finite rank 1 lattice. Now, so we get very similar behavior. So in each case, we get finitely many divergent series, and each series, if my varieties are defined to rational numbers, have algebraic coefficients. Now, so we get resonance with algebraic series with algebraic coefficients. But what's the difference between these three cases? What's the arithmetic nature of critical values? They're, in first case, they're algebraic numbers, like zero-dimensional integrals, I would say. In the second case, in the case of one forms, one-dimensional integrals, like 2 pi I or log x or whatever, and or abelian integrals. And in the case of Chern-Simons theory, you get 2 pi I squared, or maybe 2 pi squared times dialogues, are kind of two-dimensional integrals. Yeah, so it's all hints to the following. Maybe it's only just the beginning, 0, 1, 2. And maybe what we'll have, maybe it will be some kind of like three-dimensional integrals. It's like zeta of 3 or whatever. And you get finitely many periods for the three-dimensional integrals, and it will be a lattice of critical values, and we'll get resurgence for some yet unknown mathematical object. And, yeah, so from this perspective, it looks that we should go to any dimension to be something beyond known physics and mathematics. Thank you. Okay.
Thank you very much for the talk. Are there questions?
So can you decompose the cycle of unitary gauge fields in terms of Lefschetz impulse for Chern-Simons theory?
Sorry? Can you repeat again?
Can you decompose, do you know the coefficients of the decomposition of the cycle of unitary gauge fields in Lefschetz impulse for SL2C?
Yeah. Yeah.
Do you?
You want to understand why it goes on, yeah?
So I want to know what's the expansion. So if I take the 3-sphere, for example, it's probably trivial, but let's say some length space. Can I decompose it?
Yes, yeah. I have to check some examples, but should be really finite sum of integrals of Lefschetz symbols here.
Okay, do you have an efficient scheme for determining these numbers?
Without
solving Kapustin-Witten equations?
No, I explained this. Sounds it's a bit mysterious. You consider solution of Kapustin-Witten equation and set it on one side it's unitary, and another it's flat.
Yes, but that's tautology. But can one do it efficiently?
Efficiently, yes. Yeah, I think it's a resurgence. Yeah, it's some kind of. No, at least numerically, I think it will be possible to do because you get some integer numbers, and you just guess them. And
what's the second question? What's the origin of this? What are these matrices Bij in your expressions?
It's just some symmetric matrices.
Yeah, but what's the origin in the three manifold? What do you describe?
Oh, it's something encoding. I don't know, some incidence graph, whatever.
Thank you.
Triangulation, yeah. You just really go back to gory details of this. Yeah, our matrices, formulas for 6J symbols, and so on. Yeah. It's kind of completely formal. You have basis for representations. You get indices for 6J symbols, and so on.
But it looks like what these formulas are is that you have some kind of abelianization of your flat connection, and there is some kind of intersection form maybe on some two-dimensional skeleton or something.
Maybe. Yeah. No, it's really interesting to figure out what are these matrices here.
Thank you.
Yeah, they're huge. They're huge here.
Are there other questions?
I have heard from your talk, you pronounced the word of Resurgence. And can you access a bit further from the point of transferring?
Sorry, I didn't get at all your question, I have to say.
Resurgence and
Resurgence, yeah,
oui,
Resurgence.
Resurgence, can you say a bit further on this?
No, there is another source of resurgence called Ekal-Varonian series. When you consider germ of analytic diffeomorphism, like z goes to z plus z squared plus high terms, and want to conjugate to normal form, z plus z squared without high terms. The conjugation theory has factorial behavior, and presumably it's related to like normal forms of vector fields and stuff like this. I'm not really an expert in this area. Okay.
Well, it looks like there's no more questions, so let's thank Maxim again.
Okay.